Okay, I've got 3 more trig and Pythagoras examples here for you to have a look at. The first one deals with standard trig values. This comes up all the time, so it's worthwhile knowing about these and being able, even if you forget the actual values of sine 45 or tan 45, that you can very quickly work them out. Now, the 45s are generated by an isosceles triangle. So if you draw one very quickly, these are the 45s. Of course, this means that angle is the right angle. Okay, to get the standard values, you make these two sides 1. Now, Pythagoras said that the hypotenuse, let's call it z for the moment, z squared equals 1 squared plus 1 squared, which is 1 plus 1, which is equal to 2. Therefore, z is equal to the square root of 2. So we've got the length of the hypotenuse. So we can work out any of the sine, cosine, and tangent relationships obeying SOHCAHTOA, and it will give us both the answers for part 1 and part 2. Okay, we can immediately write down that sine 45, so we can pick one of the 45s. Remember, look out from the 45. That will be your opposite. SOHCAHTOA tells us that the sine ratio is described as the opposite divided by the hypotenuse. So immediately sine 45 is equal to the opposite, which is 1, divided by the hypotenuse, which is the square root of 2. And that is your first answer. And very easily now, tan 45, again, you can be this angle. Look out, there's the opposite. What do we need for tan? We need the opposite and the adjacent. Opposite is 1, and the adjacent is also 1. So tan 45 is equal to 1 over 1, which is 1. And that is the answer to the second part. Now, part B relies on the fact that you should know the standard values for the other standard angles, which is 60 and 30. If this was 60 in this triangle, this angle up here is 30 degrees. And there is another similar yellow triangle that you can draw that will give you these standard values. And it's a triangle of equal length sides. So this angle down here is 60 degrees. Now, to complete the construction, I'm going to draw a vertical line from the top of the triangle to the bottom, meeting at, guess what, a right angle. And if we pick the length of these sides to be 2, we will get the standard trig values straight away. Okay, this angle up here must be 30 degrees. And now we're really only interested in the right angle triangle that I've got most of the information on. This length up to the middle must be 1, and we can get rid of the rest of the triangle now. As with the previous triangle, we've got one side that we don't know. Let's just for a moment say that this side is length y. So using Pythagoras, I can say that 2 squared is equal to y squared plus 1 squared. So y squared, moving things round a bit, is equal to 2 squared minus 1 squared. And that's equal to 4 minus 1, which is equal to 3. Therefore, y is equal to the square root of 3. So we can pop that on our diagram. So if you're the 60 degree angle for the moment and you look out, opposite to you is root 3, alongside or adjacent to you is 1, and your hypotenuse is 2. And if you're the 30 degrees and you look out, your opposite is 1, your adjacent is root 3, and your hypotenuse is 2. And from this diagram, we can get all of the trig values that relate to 60 degrees and 30 degrees. Okay, for this question, which I must say the diagram here is incredibly badly drawn, this is nowhere near 60 degrees, but they aren't to scale, so we've just got to go with that, which is why my diagram looks incredibly different to theirs. So in terms of standard trig values, I can say that the sine of 60 degrees is equal to the opposite divided by the hypotenuse, which in this case is root 3 over 2. So cos 60 is equal to the adjacent, which is 1, divided by the hypotenuse, which is 2. So if we do exactly the same thing for the diagram in the question, sine 60 is equal to, again, be that angle, Opposite is A, so this is A over 2. And cos 60, which is B over 2. So it's going to be a very simple solution now, because all we need to do is equate the sines and the cosines, and we'll get the answers directly. So therefore, using sine 60, I can say that root 3 over 2 is equal to A over 2, which means that the over 2's disappear. Therefore, A is equal to the root of 3. And the other one, 1 over 2, must be equal to B over 2. Therefore, B is equal to 1. And those are your two answers. Okay, let's have a look at the second question. Find Q, which is this vertical length here, given that relationship. So applying Pythagoras to this triangle here with the values, we get 9 squared is equal to 7 squared plus Q squared. We need Q the subject, so we can say therefore Q squared. To leave Q on its own, we have to subtract 7 squared from both sides. So this is equal to 9 squared, which hasn't moved, minus 7 squared. Now they want us to leave the answer as a square root, because square rooting our result would mean we'd have to use a calculator. But we can at least get this into a single square root. So therefore, Q squared is equal to 9 squared is 81, and 7 squared is 49. And if we take those from each other, so this is 32. So therefore, Q equals, well, yes, plus or minus the square root of 32, but because this is a positive length, I can reject the negative solution, so I can say that Q is equal to the square root of 32. And that's your answer. Now this last question wants to find us the length of a pencil that can fit into a box 14 by 6 by 3. The longest length of the pencil that can fit into the box would be across the diagonals from bottom to top. So this is an application of 3D Pythagoras. So let's draw the box and I'll take you through the problem. And the pencil that can fit in would be from the bottom to the top, but going across the diagonal. So we've got to find that length. Now, for those of you who have not seen this before, the way you do this is to first construct a line which just goes across the bottom. So if you imagine looking down from the top, you've got a right-angled triangle on the base here. 6, 14, the right angle is here, yeah, and we've got a hypotenuse, and let's call it Z. And we've got a Pythagorean relationship between 6 and 14 and Z, which is that Z squared must equal 14 squared plus 6 squared. Now, the trick with these questions is not to calculate this out at this stage. Leave it as it is, and you'll see the reason why in a moment. Okay, now look, Z forms part of yet another triangle. This is a slice through the box. The pencil length is its hypotenuse. The base length is right along the diagonal of the base of the box, and the height of the box forms the other side. So we've got yet another right-angled triangle that will give us the length of the pencil. So let's call the length of the pencil P. We can say that P squared is equal to Z squared plus 3 squared. And here's the reason that you didn't calculate that out first, because it would have been a waste of time. Because look, we can now substitute Z squared for what we've got here, which is 14 squared plus 6 squared. So we can say that P squared is equal to 14 squared plus 6 squared plus 3 squared. And that's what I wanted to show you. The double application of Pythagoras creates a three-way squared Pythagoras of all of the sides that we know about, 14 and 6 and 3. So if you remember that, you can go straight in these sort of questions to that 3D answer. Well, now it's just a matter of working this out. And this question, we can use a calculator, and that is equal to 241. Therefore, P equals, yet again, we're taking a square root. You have to think about the negative version, but we haven't got a negative pencil length. It must be a positive pencil length. So I can say that P is equal to the square root of 241, which on a calculator is equal to 15.6 15.524. And given that these numbers are only quoted to their actual value, I think it's probably fair enough to truncate this to one decimal place. So that is equal to 15.5, three significant figures, or 1 dp. And that is your answer.